Assalamu alaikum, brothers and sisters. Welcome to the journey of Quest, where we quench your thirst of knowledge. Have you ever wondered how minerals, those inanimate objects beneath our feet, can undergo transformations similar to living organisms? Just as a caterpillar morphs into a butterfly, minerals too have their own transformative journeys. This metamorphosis, however, is not brought about by time or the elements, but by a process known as ionic substitution. Picture a bustling city, where buildings are constantly being constructed, demolished, and reconstructed. This city is a mineral, and the buildings are ions. Sometimes an ion in the mineral structure decides to pack up and leave, and a different ion moves in to take its place. This is ionic substitution, a silent, invisible dance that constantly reshapes the world beneath us. From the limestone under your feet to the diamond on a ring, every mineral has a story of transformation, and each transformation holds within it a mystery waiting to be unraveled. Let's dive into the fascinating world of ionic substitution in minerals. Let's take a closer look at how ions dance in the mineral structure. The mineral structure, a bustling city of ions, is in a constant state of flux. Picture a grand ballroom, where partners are continuously swapping. This swapping is not a haphazard jumble, but an elegant dance governed by the rules of size and charge compatibility. An ion can only replace another if it is similar in size and carries a similar charge. But why do ions swap places? It's all about achieving stability. Sometimes an ion finds that it can be more stable, more comfortable, in a different mineral structure. So it packs its bags and moves out, leaving behind a vacancy. This vacancy is quickly filled by another ion, eager to join the dance. This process of swapping places is known as ionic substitution. It's a silent, invisible dance happening right beneath our feet. But here's the fascinating part. This dance of ions is not a one-time event. It's a continuous process happening over geological timescales. From the moment a mineral is formed, the dance begins, and it continues until the mineral is weathered away. So every mineral you see around you, from the tallest mountain to the smallest grain of sand, is a grand ballroom where the dance of ions never stops. The dance of ions is a fascinating spectacle of nature, happening right beneath our feet. Temperature plays a crucial role in the dance of ions. Just as the rhythm of music controls the pace of a dance, temperature influences the movement of ions within a mineral structure. At higher temperatures, the energy levels rise, giving ions the extra push they need to move around. This increased movement facilitates the swapping of places, making ionic substitution more likely to occur. Picture the grand ballroom of ions now pulsing to a faster beat, ions swapping places in a lively tango. On the other hand, at lower temperatures, the energy levels drop. The dance of ions slows down, turning into a slow waltz, and ionic substitution becomes less frequent. The ions, lacking the energy to move around as much, tend to stay put. This is why some minerals form predominantly at high temperatures, while others form at lower temperatures. Temperature, therefore, is like the music to which the ions dance. Just like dancers respond to the rhythm of music, ions respond to the rhythm of temperature. Understanding this correlation between temperature and ionic substitution gives us further insight into how minerals evolve over time and under different geological conditions. Ionic substitution is not just a dance, but a dance with consequences. Indeed, the swapping of ions isn't just a molecular jig, but it brings about tangible changes that we can observe and even feel. For instance, consider the change in physical properties of minerals. When one ion substitutes another, it can transform the color of a mineral. For instance, the rich green of an emerald or the deep red of a ruby aren't just a treat for the eyes, they're the result of ionic substitution. The hardness of a mineral can also be altered, creating minerals as soft as talc or as hard as diamond. But the impact doesn't stop there. Ionic substitution can lead to the formation of new mineral species. Imagine the Earth as a grand stage with minerals as the performers. Over time, these performers evolve, change costumes, even change roles, adding to the diversity of Earth's mineral kingdom. This process is made possible by ionic substitution. But like any dance, ionic substitution can also have its missteps. Ionic substitution can lead to contamination of soils and waterways. When harmful ions, such as heavy metals, substitute beneficial ones, it can lead to pollution of our environment. The dance of ions, therefore, is not just a spectacle, but a dance with far-reaching implications. It's a dance that shapes our world, our resources, and our environment. So joining us as we delve deeper into this fascinating dance of ions, as we continue to unravel the mystery of ionic substitution. To understand ionic substitution, we first need to grasp the basic structure of minerals. Minerals, as we know, are natural substances formed through geological processes. But what makes them so fascinating is their microscopic makeup. Picture an intricate three-dimensional architectural blueprint. Now replace the bricks and steel with atoms and ions. That's a mineral for you on a micro level. Atoms, the building blocks of matter, come together in a highly ordered internal structure to form minerals. These atoms are arranged in a specific repeating pattern that extends in all directions. This is known as a crystal lattice. But what are ions? Well, ions are simply atoms that have either lost or gained electrons. This happens because atoms strive for stability. The loss or gain of electrons provides them with a full set of electrons in their outermost shell, giving them the stability they crave. The type of ions present and their arrangement within the crystal lattice determine the physical properties of the mineral. For example, some minerals might be hard, while others are soft. Some may be transparent, while others are opaque. Some might even have unique properties like magnetism or fluorescence. Now let's talk about the bonds that hold these ions together. These are known as ionic bonds. In an ionic bond, a metal loses electrons to become a positively charged cation, while a non-metal gains those electrons to become a negatively charged anion. The attraction between these opposite charges keeps the ions together, forming the mineral. So to sum up, a mineral's structure is like a grand architectural marvel, with atoms and ions in the place of bricks and steel. The type of ions and their arrangement determine the mineral's properties, while ionic bonds hold it all together. But here's where it gets interesting. Sometimes one type of ion can replace another in the mineral's structure. This is known as ionic substitution, and it can significantly alter the mineral's properties. Now that we have a basic understanding of minerals, we can explore the phenomenon of ionic substitution. Ionic substitution is like a dance, where one partner steps out and another steps in. Now, this dance isn't as simple as it sounds. There are certain conditions that need to be met for this substitution to occur. Let's imagine a ballroom, where the dance floor is our mineral structure, and our dancers are the ions. Just like a dance floor can only hold so many dancers, a mineral structure has a certain capacity for ions. Now, let's say an ion wants to step out and another ion wants to step in. The first consideration is size. Just like in a dance where you wouldn't substitute a waltzing couple with a whole conga line, the incoming ion has to be similar in size to the outgoing ion. If the incoming ion is too large or too small, it won't fit into the crystal structure and the dance, or in our case, the ionic substitution, won't occur. Next, we consider charge. This is like the rhythm of the dance. The charges of the incoming and outgoing ions must balance. If they don't, it would be like trying to dance a tango to a waltz rhythm. It just won't work. Finally, there's temperature. This is like the speed of the music. At higher temperatures, the dancers, or ions, have more energy to move around, making it easier for them to switch places. However, at lower temperatures, the ions aren't as energetic, making ionic substitutions less likely. It's also essential to understand that these factors, size, charge, and temperature, don't work in isolation. They work together, influencing each other. Just like in a dance, where the size of the dance floor, the rhythm of the music, and the pace all contribute to the overall performance. So, ionic substitution is not just a random event, but a carefully choreographed dance of ions. Ionic substitution is not just an interesting phenomenon, but it has profound implications for the world around us. Indeed, this seemingly simple swapping of ions within a mineral's crystal structure can change how we understand and interact with our planet in many ways. Let's start with mineral identification. Minerals are like fingerprints of the earth, each one unique and revealing about the conditions under which they formed. Ionic substitution, in its ability to alter the composition of a mineral, can sometimes create variations that are so different from the original that they are classified as a new mineral species. This means that the diversity of minerals we observe is, in part, a result of ionic substitution. Next, ionic substitution plays a crucial role in geothermometry. This is the science of determining past temperatures of geological formations from the minerals present. Specific ionic substitutions are sensitive to temperature, meaning the composition of a mineral can tell us about the temperature at which it formed. This gives us an invaluable tool for understanding past climates and predicting future ones. But the implications of ionic substitution extend beyond the realm of geology. It also has significant impacts on environmental science. For instance, some ions like lead or arsenic can substitute for other ions in minerals and then be released into the environment when the mineral weathers. This can lead to contamination of soils and waterways, posing risks to human health and ecosystems. Understanding these processes is crucial for managing and mitigating environmental pollution, and that's just scratching the surface. With ongoing research, who knows what other implications of ionic substitution we'll discover? From the tiniest grain of sand to the tallest mountain peak, from the depths of the ocean to the furthest reaches of space, ionic substitution is at work, silently shaping the world in ways we are only just beginning to comprehend. Ionic substitution, therefore, is a key player in shaping our world and our understanding of it. Let's summarize what we've learned about ionic substitution in minerals. In our journey to understanding this phenomenon, we started by unveiling the mystery that is ionic substitution. We learned that it's a natural process, occurring within the lattice structures of minerals. This process involves one ion replacing another of similar size and charge. It's like a dance where every step is precise, every move intentional. We also discussed how minerals, those naturally occurring, inorganic solid substances, are the playing field for this ionic dance. Each mineral, with its unique lattice structure, provides a different stage, influencing the patterns and rhythms of the ionic substitution. Peeling back the layers, we delved into ionic substitution itself, exploring the intricacies of this process. We discovered that not all ions can swap places. They must be similar enough in size and charge. It's a delicate balance, a careful selection, ensuring the stability of the mineral structure. We then looked at the implications of ionic substitution. It's not just an intriguing scientific phenomenon, it has real-world impacts. It can affect the color, hardness, and even the magnetic properties of minerals. This process, in turn, influences the way we use these minerals in everyday life, from construction materials to cosmetic products. So let's take a moment to appreciate this dance of ions. It's a process that happens on a scale so small we can't see it, yet it shapes the world around us in ways we can't ignore. It's a silent symphony, a ballet of atoms choreographed by the laws of nature. Ionic substitution, a dance of ions, is not just a fascinating scientific phenomenon, but an integral part of our world. So next time you see a mineral, remember the intricate dance happening within it. Thanks for watching us share our videos. Subscribe our YouTube channel and press the bell icon and stay curious for new uploads.